Hi class, today we're going to take a look at rational exponents. A rational exponent is when you have a fraction for your exponent on your base that you have here. It can be a number, it could be a letter, it won't really matter. But this here is going to be a fraction, so m and n will be numbers in most cases. When we take a look at this, what you want to notice is that this fraction, the denominator of it, is actually telling you that you have a root, which means you're doing a root of something raised to the exponent, which is the numerator. So you'll want to take note that in this rule, the root here is always going to be the denominator of your fractional exponent, and the exponent here is going to be the numerator of that fractional exponent, and that will always be the case. Another way to write the same exact thing is like you see right here. In this, notice that we still have an nth root here, and the n is still the denominator of our exponent. And then we, instead of having the n as your exponent on your x, it's the exponent on the entire expression. But the n still goes to your numerator. The reason why we're able to write both these expressions so that they're equivalent is because you have a power to a power exponent rule that says that if you have something raised to a power raised to another power, that you multiply those exponents. And in this case, if we're looking at a fraction, I need the outside exponent 1 over n. If we were to multiply these, we would get straight back to what we have here. Similarly, if we had the 1 over n as our exponent in here with the m as our outer exponent, and when we put this over 1 and we multiply, we get straight back to here. Either way it works, what you want to do is choose which way is going to make your problem the easiest. So for instance, if we take a look at this particular problem here, we have 8 to the 2/3. We could either use the 2 and square the 8 to get 64 and then cube root it, or if we want to keep our numbers small, we can cube root the 8 first and then square it. I prefer to keep my numbers smaller. We will get the same answer no matter which way we choose to do the problem. So I'm going to go ahead and switch this into the cube root of 8 so I can keep the number smaller, and then we will square it using the rules that we have up on the top. The cube root of 8 right here turns into 2 because 2 times itself 3 times is 8. And then we can square it and we get our final answer of 4. So that's how we could use this rule to help us solve that without needing a calculator. Similarly, we could also have done this 8 to the 2/3 as squaring 8 and then cube rooting it. If you square 8, you get 64. And the cube root of 64 is 4 because 4 times itself 3 times is 64. So that's how you can deal with those. Now this rule can make some problems that we previously would have thought we couldn't do possible. For instance, if we have, say, the 5th root of x to the 4th, and we're multiplying it by the cube root of x squared, in previous things that we've learned, we would say that we could not do anything with this because the roots are different. This is a 5th root and this is a cube root. In order to be able to multiply these together, both roots have to be the same. Now that we have fractional exponents, that's actually not the case. You can change this into a fractional exponent and write it as x to the 4/5. And you can write this as a fractional exponent and make it x to the 2/3. Notice that the root of 5 here is in the denominator, and the root of 3 here is also in the denominator. Once you do that, you can use our rule that if your bases are the same, which both of these are x's, you're able to add the exponent. So this becomes x to the 4/5 plus 2/3. And we can add 4/5 and 2/3. In order to add them, we need common denominator. So I'm going to multiply top and bottom here by 3 to make a common denominator of 15. On top and bottom here by 5 in order to make a common denominator of 15 there. This changes this into x to the 12/15 plus 10/15. That we're able to add, and this becomes x to the 22/15. Now we can go ahead and, since we started in radical form, switch this back into radical form. When you do that, you can go ahead and just switch it and then simplify, or you can recognize that this right here is an improper fraction. If we were to write it as a mixed number, it would be 1 7/15, which means this is really x to the first times x to the 7/15. X to the first can stay out here, and then if we just do our radical using this turns into x times the 15th root of x to the 7th, and that would be our simplified form. Now you could have similarly gotten the same answer by staying with 22/15 and changing this into the 15th root of x to the 22nd. Yet you would have needed to know that this was not simplified, and we had a nice little trick that you could take this root and divide it into the exponent here. And 15 goes into 22 once, which would make it so you have 1x outside your radical. And when you divide 15 into 22, there's 7 left over, so there would be an x to the 7th underneath. The reason why this dividing of this root into the exponent works is because of what we see over here. If this was not the case, we wouldn't be able to do that. But because you can switch this into a mixed number and use the exponent rules to pull out the x to the first, this little trick over here works. Both give you the same answer, whichever one you prefer is fine. Let's look at one more type of problem that in previous situations we would have thought we couldn't do. So let's say that you had r to the 1/3, and you're multiplying it by r plus r to the 2/3. You can do this the same way, distributing this. You need to recognize that there's a 1 right here, and 1 is the same thing as 3/3. So if you add those, you get r to the 4/3. Plus, if you distribute this across here, adding those exponents, 1/3 plus 2/3 is r to the 3/3, or r to the first. Yet we don't need to write that one, you can just leave it like that. And then you can simplify this first one if you want to turn it back into radical form and say, well, 4/3 is the same thing as 1 and 1/3. That means that you'll have 1 r up front, and you'll have 1 r under your cube root. And this would be your simplified form for that particular problem. Let's take a look at one more type of problem. Let's say you have something where you're dividing. And for instance, you have square root of 81x, and you're dividing it by the fourth root of x cubed. At first glance, you would say, well, we can't do anything because if you look at this is a square root and this is a fourth root. They have to be the same root in order to do anything. However, we can do a little bit. To start out with, the square root of 81 is 9, so I can put a 9 in front of that and do the actual square root of 81 to get 9. That will be over your fourth root of x cubed. Now, if we switch to fractional exponents at this point, we can actually take care of the radicals. The 9 will stay the same, but this x, when we have a square root, there's a little invisible 2, you can imagine, in that little b part of the beginning of the radical. So this is really a 1/2 exponent. In the denominator, if we go to fractional exponents, that's a 3/4. Now, since the x's are like bases, we can go ahead and use our rule as x to subtract those. So this is 9 times x to the 1/2 minus 3/4. The common denominator for them is going to be 4. So I'm going to multiply this top and bottom here by 2, which is going to give me a 2/4. So this is really 2/4 minus 3/4 for my exponent. That's going to make this, so this is 9 times x to the 2 minus 3 becomes -1, so -1/4. Using our negative exponent rule, we will take our x and put it to the bottom and make that a positive, and then we can go back to radical form, making this a fourth root of x in the denominator. So previous problems where the radicals were not the same root, since we have this fractional exponent rule, we are now able to actually do those.